Boise State, you may begin.
Hello, everyone. Thank you for joining. We are from Boise State University, and we have the district use case of Lake Nona Town Center. Our team is comprised of electrical engineers and mechanical engineers. For electrical, we have Haley, Chris, myself, Christopher, Jacob, and for the mechanical, we have John, Andrew, Nolan, and David. Our advisors and mentors are Aaron, Brian, Andreas, and Shelby. Our team was challenged to design a solar photovoltaic system and a battery backup system for the Lake Nona Town Center. The red line is the boundaries, and within those boundaries, we had 7 buildings and 1 open field. And we were also allowed to use any of the surrounding bodies of water. The team decided not to put any solar panels on the HQ garage, the Wave Hotel, the chiller plant, or any of the bodies of water. And this is because the bodies of water and the HQ garage was not financially feasible. While the Wave Hotel, we had limited rooftop space, and the chiller plant had little information and was currently under construction. With the 4 buildings and the open area, we were able to produce 2 gigawatts of power a year. Our team's design, what we did on all of them, we have all of our panels facing 165 degrees azimuth, and all the buildings have a tilt of about 28 degrees, with our open field having a single axis tracking system. All of our inverters are placed on the north side of a building and in shade, while the open field have our inverters underneath a shade. This is to help with overheating. To maximize energy production of each building and to not add unnecessary cost, we set a solar access percentage of 90%. So if an area did not meet the 90%, we did not put any solar panels in that area.
And then for the second section of this design project, a battery energy storage system was added to the HQ building to help with voltage regulation, peak shaving, PV smoothing, and system resilience. We started by sizing the battery system using the NREL Reopt online tool. Using the HQ's building's energy use profile, we found a recommended battery size of 1.8 megawatt hours. So, however, to add some headroom and resilience, we opted to find a 2 megawatt hour storage system. The team decided to install the batteries in an external enclosure next to the HQ office building as a safety measure to prevent a fire from extending to the building in the event of a thermal runaway. This container will be placed in close proximity to the outside of the HQ building. Its specific location is flexible and can be left up to Lake Nona Town Center due to the building being under construction and the lack of information on the space available for the pre-built system. The team also used lithium iron phosphate batteries because of their high thermal runaway temperature. This battery chemistry would best serve the district's needs because they are safer, require less maintenance, and tend to have a longer lifespan. Overall, this solar and battery storage system will add resilience and help offset the money spent on energy during hours of peak usage. And then our battery expected operation was found using SAM, and it's displayed in this table with a minimum state of charge at 30%, a maximum state of charge at 95%, an initial state of charge at 50%, and then the minimum time at charge state would be 10 minutes.
Many factors were considered regarding the distribution impact that our systems may have on the main power grid. We considered voltage impact, protective devices, short circuit studies, and islanding conditions. Looking at the heat map, the maximum energy that we can return to the grid at the location of our systems is 2,500 kVA. According to the SAM simulations, our systems produce no excess energy, so we're not concerned about overloading feeders or power curtailment at this time. We used the OpenDSS simulation to measure the impact that our systems had on voltage levels, and the voltages measured at our system's interconnection point maintained the ANSI range A of 291 volts to 263 volts. However, when considering distance, the voltage goes out of range, so we used a cable and voltage drop calculator to find the minimum cable size needed for our systems. As you can see, most of our buildings require 0 gauge cable sizing, except for the open field, which when connected to the Wave Hotel requires a cable size of 350 kc mil. We designed our PV systems with protective switches and reclosers to provide protection to sensitive components on both sides of interconnection. Theoretically, short circuit studies will be needed to ensure these switches are rated to the capacities required for our systems. These components allow our systems to island during power outages and to prevent energizing the grid while still providing energy to the load. And upon re-energization and no faults detected, the reclosers will reconnect the PV systems to the grid.
Okay, to go over the financial analysis for our systems, we used the provided financial model for all of our developer side finances and Energy Toolbase for all of our customer side finances. So to go over a couple of key terms, we calculated an IRR for each system, which estimates the profitability of an investment. We calculated an NPV for each of our systems, which captures the value of an investment opportunity at any given year. We found a PPA price, which is typically a long-term energy supply agreement between two parties, usually an energy producer and an energy consumer. So the tax credits that we used to try and build our savings were an investment tax credit at its base rate of 30%. And the makers benefit with a 60% bonus depreciation because our development plan showed that we could have our system in use in 2024. So we set our targets for our IRR and NPV at 5.64% based off of a meeting we had with our SDC mentor and an NPV target of 0% from the contest requirements. So from the financial model, we had a separate model for each of our systems, and we have only the HQ building meeting its targets for IRR and NPV, with the office building 2 having a slightly negative IRR for the developer, and the open fields office building 2 and garage G having negative NPVs. When we used Energy Toolbase to calculate all of our customer side finances, the HQ building and office building 1 were able to meet their targets, with the open field and office building 2 and garage G having a negative NPV. The open field does have a very high internal rate of return for the customer, but the large end of term buyout and operations costs turned the NPV negative. So the financial model inputs that we used, we had a separate financial model for each of our systems, but in total, they were about 1.3 megawatts DC. Our system costs were $1.56 per watt DC for the roof mounts and $1.64 per watt DC from the ground mounts. And those were taken from an NREL benchmarking document. Our PPA price, which was then used to calculate lease prices, was set at 9.8 cents per watt DC with a 2.5% escalation rate. And our utility price, which we found researching the OUC's rate scheduling documents, was 6 cents per kilowatt per watt DC. So to calculate our monthly leases, because Florida does not allow PPAs, we used this formula, which was provided during a webinar, and we used a lease term of 25 years. The assumption from the competition was 20 years, but based off of a previously recorded webinar, we moved it to 25 to try and stretch our savings a bit. So just a quick graph of the PPA price versus the utility price. Because the PPA price is higher and they escalate at similar rates, the PPA fails to undercut the utility cost of energy at any term. And we have a table here showing our calculated monthly leases for each of our systems, in addition to an upfront payment for each of them, which was found on a trial and error method using Energy Toolbase. and an end of term buyout for each system, which was set at 20% of the construction cost of each system. So the customer savings, the tax incentives for all the systems expire in year 6 of the term, and they all incur an O&M expense in year 16. And the cumulative cash flow for each of the systems is shown in this table. The HQ building and office building 1, the cumulative cash flow becomes negative in year 16, and those were our systems where the savings lasted the longest. So we just have a graph for the HQ building, our best performing building, with total cash flow and cumulative cash flow. And you can see that in year 16, when it incurs that O&M cost is when it begins to trend more negative. So in summary, the PPA price is significantly higher than the utility price. So the electric savings do not significantly offset the lease payments, but the system has other economic benefits, including peak shaving using the battery, increased resilience to blackouts, and a reduced energy demand from the utility.
For the development plan, we designed solar arrays for 6 locations within the Lake Nona Town Center, this being Garage G, LNTC Office Building 2, LNTC Office Building 1, HQ Buildings C and B, and the open field. For land use and zoning, the LNTC is within Orange County jurisdiction within the city limits of Orlando, Florida. All sites in the LNTC are categorized as planned developments. There's minimal land preparation needed and no restrictions for historic, environmental, residential, etc. on the production. There are size restrictions on the building additions. The photovoltaic arrays cannot exceed the maximum height of the buildings. As well as in the open field, there's a limit of 8 feet for the PV arrays, as well as a required 6-foot opaque fence surrounding the enclosure. For permitting and building codes, for interconnection, we need to follow IEEE standard 1547. For circuit inverters, controllers, and other components, that falls under photovoltaic systems article 690. And then there are permit checklists required, as this is a system of over $2,500 in the state of Florida. You need a photovoltaic permit, as well as a state licensed engineer and county inspector to sign off. For the construction timeline, we have a proposed construction timeline of 9 months with an additional month, depending on the availability of needed services. The construction is broken into 5 sections. The first being site planning, in which most of the permitting is acquired. Site construction, which consists of installing the mounting and electrical wiring. Traffic redirection and transportation of the PV systems to the rooftops. This requires cranes. Solar testing, in which we make sure that we meet IEEE standards, get a power estimate, as well as meeting fire codes and electrical inspections. And lastly is project financing, in which we need to secure a financing contract and insurance for the system. Here is a brief visual breakdown of our timeline diagram that shows all of the tasks needed and their dependencies. And then possible risks and delays in the timeline. So there is a high elevation of working on the rooftops associated with installing solar on those rooftops, which could lead to damage of equipment or personnel risk if not following proper OSHA standards. The improper use of equipment could also be an issue when transferring these solar arrays to the rooftops, which could lead to damaged solar panels. Possible delays are in the procurement of equipment. There could be delays in the procurement of things such as cranes or the delivery of the solar systems themselves, as well as the battery. And then other delays could be due to extreme weather conditions in which we would have to halt construction. Lastly is equity and community involvement. As far as social equity, this job will create a high skilled labor force. If the LNTC does give consideration to who it contracts out to, we believe that they could find a contractor based in an underserved community within the area, which would increase that community's internal revenue flow. There would also be an increase in green energy and a reduction of grid electricity usage, which would decrease demand on the grid, as well as decreasing associated carbon cost. And then community involvement, if marketed correctly, because the LNTC is a modern community with high energy usage, the use of green solar energy could lead to a guilt-free involvement with the LNTC's businesses and services from the community, where they do not need to consider that high electricity usage.
Okay, thank you, Boise State. That is all the time we've got.